Welcome to Science for Sleep, where wonder and calm meet. Each night we drift through galaxies, oceans, and mysteries of the natural world, not to startle, but to soothe. So, take a deep breath. Let curiosity slow your thoughts, and fall asleep to the sound of discovery. The deepest secrets about Mariana Trench, the deepest place on Earth. Our planet is a world of explored frontiers. We have scaled its highest peaks, traversed its most arid deserts, and mapped its continents in exhaustive detail. From the vantage point of space, Earth appears as a familiar blue marble, its features charted and its mysteries seemingly solved. Yet this perspective is an illusion. The vast majority of our own world remains unseen, unexplored, and profoundly unknown. More than 70% of the Earth's surface is covered by water, and beneath that water lies a realm as alien and as challenging as the surface of another planet. It is a world of crushing pressure, absolute darkness, and unimaginable cold. And in this hidden world, there are depths that defy human comprehension. In the western Pacific Ocean, east of the Mariana Islands, lies the most extreme feature of this submerged world. It is a vast, crescent-shaped scar in the Earth's crust, a geological feature of immense scale and profound significance. This is the Mariana Trench, and it is home to the deepest known point on the surface of our planet. To speak of its depth is to speak in numbers that are difficult to contextualize. The trench plunges to a maximum known depth of nearly 11,000 meters, or 11 kilometers. That is almost 36,000 feet. It is a dimension of verticality that has no equal on land. The highest point on Earth, the summit of Mount Everest, stands at 8,148 meters. If one were to take Mount Everest and place it into the deepest part of the Mariana Trench, its peak would still be submerged by over 2 kilometers of water. An entire mountain range could be hidden within its depths, its peaks never troubling the surface. The trench is not merely a hole, it is a colossal geological formation. It stretches for more than 2,550 kilometers, a distance greater than the length of the Grand Canyon, and maintains an average width of only 69 kilometers. It is a long, narrow, and incredibly deep chasm, a fundamental boundary in the Earth's crust where the very fabric of our planet is being recycled. This place represents the absolute physical limit of our world's geography. It is the antithesis of space exploration. Instead of journeying outward into a vacuum, exploring the trench requires a journey inward, into a realm of ever-increasing pressure. At its bottom, the weight of the water column above exerts a pressure of over 1,000 atmospheres. This is the equivalent of 100 elephants standing on a postage stamp, or the force of a commercial jetliner being balanced on the tip of a finger. It is a pressure that can crush steel, compress materials, and extinguish life as we know it. For this reason, the Mariana Trench has captured the human imagination with a power equaled only by the allure of outer space. It is the ultimate terrestrial frontier, the last great unexplored wilderness on our own planet. It evokes a primal curiosity, a desire to know what lies in the deepest, darkest corners of our world. For centuries, the deep ocean was a realm of myth and legend, a place where sea monsters were thought to dwell, where the laws of the surface world no longer applied. While science has replaced these myths with a more complex and fascinating reality, the sense of mystery remains. The trench is a challenge, not just to our imagination, but to our technology. Reaching its bottom is a feat of engineering on par with landing on the moon. It requires a vessel capable of withstanding forces that can pulverize most submarines, and it requires a level of precision and resilience that pushes the very limits of human ingenuity. It is a place that actively resists exploration, a realm that guards its secrets with the crushing weight of an entire ocean. But it is also a place of profound scientific importance. It is a unique laboratory for studying the processes of plate tectonics, the forces that shape our planet's surface. It is a crucible for life, a place where organisms have evolved extraordinary adaptations to survive in one of the most hostile environments on Earth. And it is a stark and sobering indicator of the reach of human influence. A place where even at the deepest point on the planet, the signs of our industrial world can be found. The story of the Mariana Trench is a story of geology, of physics, of biology, and of human exploration. It is a journey into a world without light, a world of immense pressure, and a world of strange and beautiful life forms that have carved out an existence at the very edge of possibility. It is a story that forces us to redefine our understanding of the limits of life and to confront the vast and humbling extent of our own planet's hidden realms. This is not another world. This is our world, and its deepest secrets are waiting to be discovered. The geography of the abyss. The Mariana Trench is not a simple uniform chasm. It is a complex and varied geological province, a dynamic landscape with its own unique features, all sculpted by the immense forces of plate tectonics. To understand the trench is to understand its geography, a geography that exists in a realm of perpetual darkness, miles beneath the surface of the Pacific Ocean. Seen from above, if the waters of the Pacific could be drained away, the trench would appear as a great, curving arc on the seafloor. This crescent shape, stretching for over 2,550 kilometers, is a direct consequence of the geological process that forms it. It traces the boundary where the vast Pacific Plate, one of the Earth's largest tectonic plates, is being forced to bend and plunge beneath the smaller, overlying Mariana Plate. The trench is, in essence, the crease in the Earth's crust created by this colossal, slow-motion collision. While the trench is immense in length, it is surprisingly narrow. Its average width is only about 69 kilometers. This creates a V-shaped profile, a steep-sided valley that plunges to extraordinary depths. The walls of the trench are not smooth slopes, but are themselves complex geological terrains, marked by faults, canyons, and the scars of underwater landslides. The immense pressures and tectonic stresses in this region create a fractured and dynamic environment. The deepest part of the Mariana Trench, and indeed the deepest known point in any ocean on Earth, is a small, slot-shaped valley at its southern end. This specific location is known as the Challenger Deep. It was named after the British Royal Navy survey ship HMS Challenger, which made the first measurements of the trench's depth in 1875. The Challenger expedition was a landmark in the history of oceanography, and its discovery of this profound depth opened a new chapter in our understanding of the planet's geography. The Challenger Deep itself is not a single point, but a relatively flat-bottomed basin, about 11 kilometers long and 1.6 kilometers wide. Within this basin, modern high-resolution sonar mapping has identified three distinct pools: the Western Pool, the Central Pool, and the Eastern Pool. The absolute deepest point is believed to lie within the Eastern Pool, though the difference in depth between these pools is only a matter of a few tens of meters. Determining the precise depth of the Challenger Deep is an ongoing scientific challenge. The first measurements, made by the Challenger expedition, were taken using a weighted sounding rope, a simple but effective method that yielded a depth of over 8,000 meters. In 1951, the HMS Challenger 2 returned to the spot with a more modern tool, an echo sounder. By sending a pulse of sound from the ship and measuring the time it took for the echo to return from the sea floor, they were able to calculate a much more accurate depth, a value very close to the modern measurement of 11,000 meters. Today, the depth is measured using sophisticated multi-beam echo sounders mounted on research vessels, or by pressure sensors mounted on submersibles and landers that are sent to the bottom. These measurements have refined our knowledge of the trench's depth to an astonishing degree of precision. The currently accepted maximum depth is 10,984 meters, with a margin of error of only about 25 meters. This precision is a remarkable achievement, considering the immense challenges of measuring a feature through 11 kilometers of water, a medium whose temperature, salinity, and pressure all affect the speed of sound. The geography of the Mariana Trench is not limited to the trench itself. Parallel to the trench, on the overriding Mariana Plate, lies a chain of volcanic islands, the Mariana Islands, which give the trench its name. These islands are the product of the same subduction process that created the trench. As the Pacific Plate is forced downward, it heats up, and water trapped in the rock is released. This water rises into the overlying mantle, lowering its melting point and generating magma. This magma then rises to the surface, creating the volcanic arc of the Mariana Islands. Between the trench and the island arc lies another fascinating feature, a series of enigmatic mud volcanoes. These are not true volcanoes that erupt molten rock, but locations where fluids, gases, and mud from deep within the Earth's crust are forced to the surface. These fluids are rich in methane and other chemicals, and they support unique ecosystems that are not dependent on sunlight, but on the chemical energy of the Earth itself. The geography of the Mariana Trench, therefore, is the geography of a complete and active tectonic system. It is a place where new land is being created in the form of volcanic islands, and where old seafloor is being destroyed as it plunges back into the Earth's mantle. It is a dynamic and interconnected landscape, a place where the fundamental forces that shape our planet are on full and dramatic display. It is a world of extreme depths, of steep walls, of volcanic activity, and of a constant, slow, and powerful geological churn. This is the physical stage upon which the unique story of life in the deep ocean unfolds. Birth of a trench. The Mariana Trench is not a scar from a single, ancient cataclysm. It is the product of a slow, relentless, and ongoing geological process that has been shaping our planet for billions of years. The birth of the trench is a story of plate tectonics, the grand, unifying theory of modern geology. It is a story of how the Earth's rigid outer shell is broken into a mosaic of moving plates, and how the interactions at the boundaries of these plates create the most dramatic features on our planet's surface. From the highest mountains to the deepest oceans, the specific process that creates the Mariana Trench is called subduction. This occurs at a convergent plate boundary, a place where two tectonic plates are moving toward each other. In the case of the Mariana Trench, the two plates involved are the colossal Pacific Plate and the smaller, but still significant, Mariana Plate. The Pacific Plate is one of the largest and oldest sections of oceanic crust on Earth. For millions of years, it has been slowly moving northwestward, carrying the seafloor of the Pacific Ocean with it. The oceanic crust is not static. It is born at mid-ocean ridges, where molten rock from the Earth's mantle rises to the surface and solidifies. This new crust is hot and therefore relatively buoyant. But as it moves away from the mid-ocean ridge, it cools and becomes denser. It also accumulates a thick layer of sediment, which adds to its weight. After tens of millions of years of this slow journey across the ocean basin, the old, cold, and dense oceanic crust of the Pacific Plate is ready to sink. When the Pacific Plate collides with the Mariana Plate, its immense density becomes the deciding factor. It is heavier than the crust of the Mariana Plate, and it is heavier than the hot, buoyant mantle that lies beneath it. As a result, it is forced to bend and plunge downward, back into the Earth's mantle. This process of one plate diving beneath another is subduction, and the Mariana Trench is the surface expression of this great downward flexure of the Pacific Plate. The angle at which the Pacific Plate subducts beneath the Mariana Plate is unusually steep, almost vertical in some places. This is because the Pacific Plate in this region is some of the oldest oceanic crust on Earth, over 180 million years old. Its extreme age means it has had a very long time to cool and become incredibly dense, and it therefore sinks into the mantle under its own weight with very little resistance. This steep angle of subduction is one of the key reasons why the Mariana Trench is so exceptionally deep. The process of subduction is not a smooth one. As the two plates grind against each other, immense stresses build up in the rock. These stresses are periodically released in the form of earthquakes. The Mariana Trench is part of the Pacific Ring of Fire, a zone of intense seismic and volcanic activity that encircles the Pacific Ocean. The subduction zone of the Mariana Trench is capable of producing some of the most powerful earthquakes on the planet, as the immense friction between the two plates is overcome in a sudden and violent release of energy. As the Pacific Plate descends into the mantle, it begins to heat up. The water that has been trapped in the minerals of the oceanic crust is driven off. This water, being less dense than the surrounding rock, rises into the overlying mantle wedge of the Mariana Plate. The addition of water to the hot mantle rock has a crucial effect. It lowers its melting point, causing it to melt and form magma. This magma is buoyant, and it rises toward the surface. Some of it erupts on the seafloor, creating submarine volcanoes. Some of it breaks through the surface of the ocean, creating the volcanic islands of the Mariana Archipelago. This chain of volcanoes, running parallel to the trench, is a direct and visible consequence of the subduction process happening miles below. The trench and the volcanic arc are two sides of the same geological coin. One, a zone of destruction where crust is consumed. The other, a zone of creation where new land is born. The birth of the Mariana Trench is therefore a story of cosmic recycling. It is the place where the Earth's surface is returned to its interior, a key part of the great slow-motion convection cycle that drives the engine of our planet. The material that is subducted into the mantle at the Mariana Trench will, over millions of years, be mixed and heated and may one day rise again at a mid-ocean ridge or a volcanic hotspot to form new crust. The trench is not just a feature on the Earth's surface, it is a gateway to the Earth's deep interior, a place where the life cycle of the very rock that makes up our world is played out on a grand and majestic scale. The crushing pressure. To journey into the Mariana Trench is to enter a realm governed by a physical force of almost unimaginable power, hydrostatic pressure. It is this force, more than the darkness or the cold, that defines the trench as one of the most extreme and hostile environments on Earth. Understanding the nature of this pressure and its effects on matter and on life is the key to understanding the fundamental challenge of exploring the deep ocean. At the surface of the ocean, we live under a pressure of 1 atmosphere. This is the weight of the Earth's entire atmosphere, a column of air stretching hundreds of kilometers above us, pressing down on every square inch of our bodies. We are adapted to this pressure, and we do not feel it. But as one descends into the ocean, the pressure increases dramatically. Water is far denser than air, and the weight of the water column adds up quickly. For every 10 meters of descent, the pressure increases by 1 additional atmosphere. At 100 meters, the pressure is 10 times that of the surface. At 1,000 meters, it is 100 times. By the time one reaches the bottom of the Mariana Trench, at a depth of nearly 11,000 meters, the pressure is over 100 times that of the surface. It is a pressure of more than 100 atmospheres, or over 16,000 pounds per square inch. To visualize this, imagine a column of water 11 kilometers high, resting on a surface the size of a human thumbnail. The force exerted by that column is equivalent to the weight of a large truck. Any object or organism that exists at this depth must be able to withstand this immense and relentless, crushing force from all directions. For any object that contains an air-filled space, such as a human body or a conventional submarine, a journey to this depth would be catastrophic. The immense external pressure would cause the air-filled spaces to collapse violently. A standard military submarine, built of high-strength steel, has a crush depth of less than 1,000 meters. At the bottom of the Mariana Trench, it would be instantaneously and completely destroyed, its hull imploding with the force of an explosion. This is why any vehicle designed for human exploration of the trench must be a marvel of materials science and engineering. The crew must be protected within a sphere of incredibly strong material, typically a high-grade titanium alloy, with walls several inches thick. This sphere must be perfectly machined, with no weak points, as any flaw in its structure would become a fatal point of failure under the extreme pressure. The effects of this pressure are not limited to macroscopic structures. It also has profound effects on the very chemistry of life. Pressure favors processes that result in a smaller volume. It can compress the delicate, three-dimensional structures of proteins and other biological molecules, altering their shape and preventing them from functioning correctly. The cell membranes that enclose all living cells, which are fluid and flexible at the surface, can become stiff and waxy under extreme pressure, hindering the transport of nutrients and waste. Life in the trench has therefore had to evolve a host of remarkable biochemical adaptations to cope with this environment. The cell membranes of deep-sea organisms are rich in unsaturated fatty acids, which helps to maintain their fluidity under pressure. They have also evolved special proteins called piezolites, which are small organic molecules that help to stabilize the structure of their other proteins and prevent them from being crushed. These adaptations are a testament to the incredible plasticity of life, its ability to find solutions to even the most extreme environmental challenges. But even with these adaptations, there are limits. The pressure at the bottom of the Mariana Trench is so great that it appears to set a fundamental limit for certain forms of life. For example, fish are not found below about 400 meters. It is believed that at pressures greater than this, the function of certain key proteins required for fish physiology becomes impossible, no matter the adaptation. The trench is a natural laboratory for studying the absolute physical limits of life as we know it. The crushing pressure of the Mariana Trench is a constant and powerful reminder of the immense power of the natural world. It is a force that has shaped the geology, the chemistry, and the biology of this unique environment. It is the primary obstacle to our exploration of this realm, and it is the primary driver of the extraordinary evolution that has taken place within it. To understand the trench is to understand the profound and transformative power of pressure. The first descent. For most of human history, the bottom of the deep ocean was a place of pure speculation. It was a realm beyond the reach of technology, a void on our maps as mysterious and as inaccessible as the surface of the moon. But in the mid-20th century, a new era of exploration began, driven by a desire to conquer the last remaining frontiers on our own planet. This ambition culminated on January 23, 1960, in a mission that would forever change our relationship with the deep sea. This was the day that humanity first touched the bottom of the world. The vessel that would undertake this historic journey was the bathyscaphe Trieste. It was not a submarine in the conventional sense, but a vehicle of a completely different design, conceived specifically for extreme depth diving. The name bathyscaphe means deep boat, and the Trieste was the brainchild of the Swiss physicist and inventor Auguste Piccard, a man who had already conquered the stratosphere in a pressurized balloon. He applied the same principles of a pressurized cabin and a separate buoyancy system to the challenge of deep-sea exploration. The Trieste consisted of two main components. The first was a massive float, over 15 meters long, filled with 85,000 liters of gasoline. Gasoline was used for buoyancy because it is lighter than water, and crucially, it is virtually incompressible, meaning it would not be crushed by the extreme pressure. The second component was the crew cabin, a heavy steel sphere suspended beneath the float. This sphere, with walls 12.7 centimeters thick, was designed to protect its occupants from the crushing force of the deep. It was a tiny, cramped space, just 2 meters in diameter, with a single small porthole made of conical plexiglass. The mission, part of the U.S. Navy's Project Necton, was crewed by two men. One was Jacques Piccard, the son of the Trieste's inventor, a brilliant engineer who had helped to design and build the vessel. The other was U.S. Navy Lieutenant Don Walsh, a career submariner with a deep understanding of the ocean environment. Together, these two men would pilot the Trieste on its unprecedented journey into the Challenger Deep. The descent began on that January morning, a slow and patient journey into the abyss. The Trieste was a free diving vehicle, descending under its own weight. To go down, it carried tons of iron pellets as ballast, held in place by electromagnets. To ascend, these magnets would be switched off, and the ballast would be released. The descent was a journey through layers of ever-increasing darkness and cold. For nearly 5 hours, Piccard and Walsh watched as the light from the surface faded to a deep blue, then to a faint violet, and finally to an absolute and total blackness, a darkness more profound than any night on Earth. The temperature inside the sphere dropped to just a few degrees above freezing. During the descent, they were subjected to the immense and growing pressure of the deep. At one point, a loud crack echoed through the hull. It was the sound of the outer pane of the plexiglass porthole cracking under the strain. For a tense moment, the fate of the mission and of the two men hung in the balance. But the inner, conical structure of the window was designed to withstand such a failure, and the descent continued. Finally, after a journey of almost 11 kilometers, a faint, white shape appeared on their sonar. It was the bottom. With a gentle bump, the Trieste touched down on the fine, diatomaceous ooze of the Challenger Deep. They had reached the deepest point on Earth. The pressure outside was over 100 atmospheres. They had proven that a human-crewed vehicle could survive the journey. Peering out of the small porthole, they illuminated the abyssal plain with the Trieste's powerful lights. What they saw in their brief time on the bottom would become a subject of scientific debate for decades. Piccard and Walsh reported seeing what they believed to be a flat fish, a soul-like creature, moving slowly on the seafloor. This observation was of immense significance. It suggested that complex, vertebrate life could exist at these extreme pressures, a possibility that many biologists had thought unlikely, while later analysis would suggest that what they saw might have been a sea cucumber or another invertebrate. The report from the Trieste was a powerful catalyst for the study of life in the Hadal zone. After just 20 minutes on the bottom, their time was up. They released the iron ballast, and the Trieste began its slow 3.5-hour ascent back to the world of light and air. When they breached the surface, they had accomplished one of the great feats of 20th century exploration. They had journeyed to a place more remote and more hostile than the summit of Everest. They had proven that the deepest part of our planet was within human reach. The first ascent was a triumph of engineering, of courage, and of the enduring human spirit of exploration. It was a moment that opened the door to the abyss and forever changed our understanding of our own world. 50 years of silence. The triumphant 1960 descent of the Trieste to the bottom of the Challenger Deep was a landmark moment in human exploration. It was a feat that captured the world's imagination, a demonstration of technological prowess that seemed to herald a new age of deep-sea discovery. It was widely assumed that this first daring journey would be followed by a steady stream of missions, that humanity would quickly build on this success and make the deepest parts of the ocean a regular destination for scientific research. But this was not to be. After the Trieste's historic dive to Mons, an astonishing 52 years would pass before another human being would return to the bottom of the Mariana Trench. This half-century of silence is a story in itself, a testament to the immense and enduring challenges of exploring the Hadal zone. The primary reason for this long hiatus was a shift in national and scientific priorities. The 1960s was the dawn of the space race. The public and political imagination, and with it, the vast resources of government funding, were captivated by the challenge of sending a man to the moon. The journey outward, into the vacuum of space, became the defining exploratory goal of the era. The journey inward, into the crushing pressure of the deep ocean, was seen as a less glamorous and perhaps less strategically important endeavor. The Trieste's mission was a success, but it was a success that was quickly overshadowed by the drama of the Apollo program. There were also fundamental technological and financial hurdles. The Trieste, while a brilliant proof of concept, was a cumbersome and limited vehicle. It was slow, difficult to maneuver, and had very little capacity for scientific instrumentation. It was, in essence, a deep-sea elevator, capable of going down and coming back up, but not much else. Building a more sophisticated, scientifically capable vehicle that could operate at these depths would require a massive investment in new materials, new technologies, and new engineering solutions. In the post-Apollo era of tightening budgets, the will to make such an investment was simply not there. The scientific community itself was divided on the best way to explore the deep ocean. Many argued that human-crewed submersibles were an expensive and inefficient way to do science. They contended that the future of deep-sea exploration lay not with putting humans in the deep, but with sending robots. The development of remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, became a major focus of oceanographic research. These robotic vehicles could be deployed from a surface ship, could stay down for much longer than a human-crewed sub, and could be equipped with a wide array of cameras, sensors, and sampling tools. And, most importantly, they did not put human lives at risk. During this 52-year period, our understanding of the deep ocean was, in fact, revolutionized by these robotic explorers. Uncrewed vehicles like the Japanese ROV Kaiko and the American AUV Nereus made multiple successful dives to the bottom of the Challenger Deep. They brought back the first high-definition video of the Hadal environment, collected the first geological samples from the trench floor, and discovered a host of new species. They proved that a great deal of valuable science could be done without the need for a human presence on the seafloor. However, there were still those who believed in the unique value of human exploration. They argued that no robot could ever replace the intuitive and adaptive intelligence of a human observer. A human pilot could react to unexpected discoveries, make real-time decisions, and provide a context and a narrative for the experience of exploration that a robot could not. The dream of returning to the bottom of the trench did not die. It simply went dormant, kept alive by a small community of dedicated engineers, explorers, and visionaries. Several attempts were made during this period to build a new generation of human-crewed, full ocean-depth submersibles. But they all ultimately failed due to a lack of funding or insurmountable technical challenges. The deep ocean, it seemed, was simply too difficult and too expensive, a frontier to conquer on a regular basis. This long 52 years silence is a crucial part of the story of the Mariana Trench. It is a period that highlights the immense and often underappreciated difficulty of deep-sea exploration. It is a story of shifting priorities, of technological debates, and of the persistent and ultimately successful dream of returning to the deepest place on Earth. The silence was not an admission of defeat, but a long and necessary period of gestation. A time when the tools, the knowledge, and the will to undertake the next great journey into the abyss were slowly and patiently being assembled. Cameron's solo journey. The 52-year human absence from the Challenger Deep was finally broken on March 26, 2012. The mission, a private venture funded and led by the Canadian filmmaker and explorer James Cameron, was a radical departure from the government-led expeditions of the past. It was a testament to the power of individual vision and a new, more entrepreneurial approach to exploration. The journey was not just a return to the bottom of the world. It was a reinvention of the technology and the philosophy of deep-sea diving. The vehicle that Cameron piloted was the Deep-Sea Challenger, a submersible of a completely novel design. Unlike the bulky, horizontal form of the Trieste, the Deep-Sea Challenger was a sleek, vertical craft, a vertical torpedo designed to descend and ascend as quickly and as efficiently as possible. Its shape was a direct response to the primary challenge of Hadal exploration: the immense amount of time it takes to travel through 11 kilometers of water. By minimizing drag and maximizing speed, Cameron's team was able to cut the descent time from the Trieste's 5 hours to just 2.5. The submersible was a marvel of materials science and compact engineering. The core of the vehicle was the pilot's sphere, a small 1.1 meter diameter space made of high-strength steel. This was the only part of the submersible that was subjected to the full 1 atmosphere pressure differential. The rest of the vehicle's main structure was a beam of a revolutionary new material called syntactic foam. This was a composite of glass microspheres embedded in an epoxy resin, a material that was both incredibly strong and positively buoyant, providing the submersible's lift without the need for a flammable gasoline float like the Trieste. The Deep-Sea Challenger was not just a vehicle for reaching the bottom. It was a fully equipped scientific platform. It was outfitted with multiple high-definition 3D cameras, a suite of powerful LED lights, a robotic arm for collecting samples, and a variety of sensors for measuring temperature, salinity, and pressure. Cameron's goal was not just to get to the bottom, but to do meaningful science when he got there. He was both pilot and scientist, a one-man exploration team. The solo nature of the dive was another radical departure from previous missions. Cameron would be alone in the pilot sphere for the entire 7-hour mission, a feat of physical and psychological endurance. This decision was driven by a desire to maximize the scientific payload and to create a more intimate and personal experience of exploration. It was a return to the spirit of the lone adventurer, a single human being confronting the vastness of the unknown. The descent was a carefully choreographed and intensely focused experience. As the deep-sea Challenger plunged into the darkness, Cameron was in constant communication with his surface team, monitoring the vehicle's systems and preparing for his time on the bottom. The journey was a descent through the layers of the ocean's biology, from the sunlit waters of the surface to the strange, bioluminescent creatures of the midwater, and finally, to the profound and utter blackness of the Hadal Zone. Upon reaching the bottom, Cameron spent 3 hours exploring the floor of the Challenger Deep. This was a significant increase from the Trieste's brief 20-minute stay. He piloted the submersible across the abyssal plain, observing the geology and searching for signs of life. He used the robotic arm to collect a sample of the sediment, and he documented the entire experience with his state-of-the-art 3D cameras, capturing images of a quality and a clarity that had never before been possible. What he saw was a landscape that was both starkly beautiful and surprisingly active. The seafloor was not a barren desert, but a soft, undulating plain of fine, pale sediment. He observed strange, filamentous mats of bacteria, and he documented the presence of small, shrimp-like crustaceans known as amphipods, confirming that even at the deepest point on Earth, a complex ecosystem was thriving. Cameron's solo journey was a landmark achievement. It was a demonstration of a new, more agile, and more scientifically focused approach to deep-sea exploration. It proved that a private individual, driven by a passion for science and discovery, could accomplish what governments had been unable or unwilling to do for half a century. The mission brought back a wealth of new data, new samples, and stunning new imagery, reigniting public interest in the deep ocean and inspiring a new generation of explorers. It was a powerful statement that the age of human exploration was far from over, and that the deepest secrets of our own planet were finally and truly within our reach. The Hadal Zone. The ocean is not a uniform body of water. It is a structured and layered environment, with distinct zones defined by depth, light, temperature, and pressure. Oceanographers have classified these zones to better understand the diverse ecosystems that exist within them. The sunlit surface waters are known as the epipelagic zone. Below this lies the twilight world of the mesopelagic, and below that, the dark and cold midnight zone of the bathypelagic. Deeper still is the abyssopelagic, or abyssal zone, a realm of crushing pressure that extends from 4,000 to 6,000 meters. For many years, this was thought to be the final frontier, the bottom of the oceanic world. But we now know that there is a realm even deeper, a world within a world, that exists only in the great ocean trenches. This is the Hadal Zone. The term Hadal is derived from Hades, the Greek god of the underworld. It is a fitting name for a realm that is more remote, more extreme, and more mysterious than any other on our planet. The Hadal Zone is formally defined as the part of the ocean below 6,000 meters. It is not a continuous, global layer like the other oceanic zones. Instead, it is a collection of isolated and disconnected habitats, found only in the 33 deep-sea trenches that have been identified around the world. The Mariana Trench contains the most extensive and the deepest Hadal environment on Earth. Life in the Hadal Zone is defined by a unique and formidable set of environmental challenges. The first is the absolute absence of sunlight. No solar radiation penetrates these depths. It is a world of perpetual and total darkness, broken only by the faint and ephemeral light of bioluminescent organisms. The second is the extreme cold. The water temperature in the Hadal Zone is consistently just a few degrees above freezing, typically between 1 and 4 degrees Celsius. The third and most dominant factor is the immense hydrostatic pressure. At 6,000 meters, the pressure is 600 times that of the surface, and it increases to over 100 times at the bottom of the Challenger Deep. This pressure governs every aspect of the geology, chemistry, and biology of the Hadal Zone. These conditions create an environment that is fundamentally different from the abyssal zone above it. While the abyssal plains are vast, flat, and relatively uniform, the Hadal Zone is characterized by steep and varied topography. The V-shaped profile of the trenches means that the Hadal environment is a world of slopes, cliffs, and narrow valleys. This complex geography creates a diversity of microhabitats, from the soft sediment of the trench floor to the hard rock of its walls. Another key feature of the Hadal Zone is its isolation. Each trench is a separate and distinct habitat, often separated from the next by hundreds or thousands of kilometers of shallower abyssal plain. This isolation has led to a high degree of endemism, meaning that many of the species found in one trench are found nowhere else on Earth. The Hadal Zone is a collection of unique and isolated evolutionary experiments, each one a testament to life's ability to adapt to the most extreme conditions. The food web in the Hadal Zone is also unique. With no sunlight for photosynthesis, the entire ecosystem is dependent on food that drifts down from the productive surface waters above. This constant, slow rain of organic material, dead plankton, fecal pellets, and the occasional carcass of a larger animal is known as marine snow. It is the primary source of energy for the Hadal food web. However, very little of the organic matter produced at the surface actually reaches these depths. Over 99% of it is consumed, decomposed, or dissolved in the water column on its long journey down. The Hadal Zone is, therefore, an environment of extreme food scarcity. However, the unique, funnel-like shape of the trenches can also act to concentrate this falling food. The steep walls of the trench can channel the marine snow and the carcasses of larger animals down into the narrow valley of the trench floor. This can make the bottom of a trench a surprisingly food-rich environment compared to the surrounding abyssal plain. This is one of the paradoxes of the Hadal Zone. It is a world of extreme scarcity, but also a world where food can be concentrated in unexpected ways. The Hadal Zone is the final frontier of marine biology. It is the least explored and the most poorly understood ecosystem on Earth. Every mission to these depths reveals new species, new adaptations, and new insights into the limits of life. It is a world that challenges our most basic assumptions about where life can exist and how it can function. It is the underworld of our planet, a realm of darkness, pressure, and profound and beautiful mystery. Life in total darkness. In the Hadal Zone of the Mariana Trench, more than 6 kilometers below the surface of the ocean, the last photons of sunlight have long since been extinguished. This is a world of absolute and perpetual darkness, a realm that has not seen the sun for billions of years. The absence of light is one of the most fundamental characteristics of this environment, and it has profound implications for the nature of life that can exist here. In a world without photosynthesis, the entire ecosystem must be built on a different foundation, a foundation of energy that is imported from the sunlit world above. or, in some rare and special cases, generated from the Earth itself. The primary source of energy for the Huddle food web is the slow and constant rain of organic material from the upper layers of the ocean. This marine snow is a complex mixture of dead phytoplankton and zooplankton, the fecal pellets of small animals, and other miscellaneous organic debris. As this material sinks through the water column, it is consumed by a host of bacteria and filter-feeding animals. By the time it reaches the Huddle zone, only a tiny fraction, less than 1% of the original organic matter remains. Life in the trench is, therefore, a life of extreme scarcity, a life based on the meager leftovers from the feast in the world above. The organisms that thrive in this environment have evolved a variety of strategies to capitalize on this scarce resource. Many are detritivores, specialists in consuming dead organic matter. The seafloor of the trench is dominated by vast numbers of small, shrimp-like crustaceans called amphipods, and by strange, slug-like creatures known as sea cucumbers. These animals are the cleanup crew of the deep sea, constantly scouring the sediment for any edible particles that have settled on the bottom. They are the foundation of the Huddle food web. Other animals are predators, feeding on the detritivores. The Mariana snailfish, the deepest living fish in the world, is a top predator in its environment, using its sensitive barbels to detect the movement of small crustaceans in the mud. The food chains in the Huddle zone are relatively simple, a direct consequence of the limited amount of energy available. Occasionally, the Huddle zone receives a massive and unpredictable windfall of food. This occurs when the carcass of a large animal, such as a whale or a large fish, sinks to the bottom. A single whale fall can deliver more organic carbon to the seafloor than decades of marine snow. These events create a temporary and intense hub of activity. Hordes of amphipods, hagfish, and other scavengers are quickly attracted to the carcass, and they can strip it to the bone in a matter of months. A whale fall is a major ecological event in the deep sea, a sudden injection of life-giving energy into a world of scarcity. But there is another, more mysterious source of energy in the deep sea, one that is completely independent of the sun. This is chemosynthesis. It is a process in which chemical energy, rather than light energy, is used to produce food. This occurs at hydrothermal vents, places on the seafloor where superheated, mineral-rich water from beneath the Earth's crust erupts into the cold ocean. These vents are oases of life in the deep sea, supporting dense communities of bacteria, tube worms, clams, and other animals. These ecosystems are based on a remarkable symbiotic relationship. The bacteria that live at these vents are chemosynthetic. They have the ability to derive energy from the chemical compounds in the vent fluid, such as hydrogen sulfide. The larger animals, like the tube worms, have no mouths or digestive systems. Instead, they have a specialized organ that is packed with these chemosynthetic bacteria. The tube worm provides the bacteria with a safe place to live and with access to the chemicals they need from the vent fluid. In return, the bacteria produce organic matter, which they share with their host. It is a perfect partnership, a way of life that is completely decoupled from the sun. While large hydrothermal vent fields have not yet been discovered in the deepest parts of the Mariana Trench, the same principle of chemosynthesis is at play in other Huddle environments, such as the mud volcanoes. Here, fluids rich in methane and other hydrocarbons seep from the seafloor, providing the chemical energy for a different kind of chemosynthetic ecosystem. The discovery of chemosynthesis was a revolution in biology. It proved that life could exist in the complete absence of sunlight, and it opened up the possibility that life could exist in a wide range of other extreme environments, both on Earth and on other worlds. Life in total darkness is a testament to the ingenuity and the resilience of the natural world. It is a world built on the faint echoes of the sunlit world above, and on the hidden chemical energy of the Earth itself. It is a world of scarcity and of opportunism, a world where life has found a way to thrive in the most unlikely of places. It is a powerful reminder that the drive to live is one of the most fundamental and most creative forces in the universe. Creatures of the deep. The Hadal zone of the Mariana Trench is not a sterile, lifeless void. It is a vibrant and surprisingly diverse ecosystem, populated by a host of strange and wonderful creatures that have evolved remarkable adaptations to survive in this world of extreme pressure, cold, and darkness. These are the true aliens of our planet. Organisms so different from the life we see on the surface that they challenge our very definition of what is possible for life to be. The most abundant and successful animals in the trench are the amphipods. These are small, shrimp-like crustaceans, and they are the dominant scavengers of the Hadal zone. They can be found in vast numbers, swarming over any piece of organic matter that falls to the seafloor. Some species of Hadal amphipods are giants of their kind, reaching sizes of over 30 centimeters, a phenomenon known as abyssal gigantism. The reasons for this are not fully understood, but it may be an adaptation to the cold temperatures and the boom and bust nature of the food supply. A larger body size may allow them to travel further in search of food and to survive for longer periods between meals. Another common inhabitant of the trench floor is the sea cucumber, or holothurian. These are slug-like echinoderms related to starfish and sea urchins. They move slowly across the sea floor, ingesting sediment and extracting the organic matter from it. They are the earthworms of the deep sea, constantly turning over and aerating the mud. Many species of Hadal sea cucumbers are almost completely transparent, their internal organs visible through their gelatinous skin. This is a common adaptation in the deep sea, where there is no need for pigment for camouflage or sun protection. Perhaps the most iconic and fascinating of the Hadal creatures is the Mariana snailfish, Pseudoliparus suirae. This small, translucent, tadpole-shaped fish holds the record for the deepest living fish ever observed, having been filmed at depths of over 8,000 meters. Its ability to survive at these depths is a marvel of biochemical engineering. Its body is almost entirely gelatinous, with no large, air-filled spaces like a swim bladder that would be crushed by the pressure. Its bones are not fully ossified, but are made of a more flexible cartilage. And its cells are filled with pezolites, small organic molecules that protect its proteins from being deformed by the immense pressure. The Mariana snailfish is the top predator in its ecosystem, feeding on the abundant amphipods. Its existence proves that complex, vertebrate life can thrive in the Hadal zone. But it also seems to define the absolute limit for that life. No fish have ever been found at depths greater than about 8,400 meters, suggesting that even the remarkable adaptations of the snailfish have their limits. In the shallower parts of the Hadal zone and in the abyssal zone just above it, a host of other strange creatures can be found. The Dumbo octopus, named for the large, ear-like fins on its head, gracefully flies through the water using these fins. The tripod fish rests on the seafloor on 3 long, stilt-like fins, waiting for small prey to drift by. The anglerfish, a creature of deep-sea nightmares, uses a bioluminescent lure to attract prey to its massive, tooth-filled mouth. Many of these animals share a common set of adaptations to life in the deep. Their bodies are often soft and gelatinous, with a high water content, which makes them less susceptible to the effects of pressure. They often have reduced or absent eyes, as there is no light to see by. Instead, they rely on other senses, such as touch, smell, and the ability to detect the faint electrical fields of other animals. And many of them are bioluminescent, capable of producing their own light for communication, for camouflage, or for predation. These creatures of the deep are not monsters. They are survivors. They are the product of millions of years of evolution in one of the most challenging environments on Earth. Each one is a unique solution to the problem of how to live in a world of crushing pressure, perpetual darkness, and extreme scarcity. They are a testament to the incredible diversity and the profound resilience of life. And they are a reminder that even in the most remote and hostile corners of our own planet, life has found a way not just to survive, but to thrive. The microbial world. While the strange and wonderful animals of the Mariana Trench often capture the imagination, the true masters of this extreme environment are the organisms that we cannot see. The Hadal Zone is a world dominated by microbes. Bacteria, archaea, and other single-celled organisms are the foundation of the trench's ecosystem, and they play a crucial role in driving its biogeochemical cycles. The study of this microbial world is revealing a hidden biosphere of incredible diversity and resilience, and it is pushing the boundaries of our understanding of where life can exist. Microbes are found throughout the water column of the trench and in the soft sediment of its floor. The abundance of these microbes is surprisingly high, often rivaling the microbial densities found in much shallower, more food-rich environments. This is another paradox of the Hadal Zone. Despite the extreme scarcity of food falling from above, the seafloor is teeming with microbial life. This suggests that these organisms are incredibly efficient at scavenging and utilizing the limited resources that are available. The microbes of the Mariana Trench are not the same as those found in the surface world. They are extremophiles, organisms that are adapted to thrive in conditions that would be lethal to most other forms of life. The most important adaptation for life in the trench is the ability to withstand extreme pressure. These organisms are known as barophiles or piezophiles, meaning pressure lovers. Barophilic microbes have evolved a host of biochemical adaptations to maintain their cellular function under thousands of atmospheres of pressure. Their cell membranes are composed of special lipids that remain fluid and functional, where a normal cell membrane would become rigid and impermeable. Their proteins are structured in a way that is inherently more stable and resistant to being compressed and denatured. Some of them even require high pressure to function correctly. They cannot survive at the surface. One of the most remarkable discoveries in the Mariana Trench is the sheer diversity of this microbial life. By analyzing the genetic material extracted from sediment samples, scientists have identified thousands of distinct microbial species, many of which are new to science. This hidden biodiversity is a vast and largely untapped reservoir of novel genes and biochemical capabilities. It is a genetic library that has been shaped by millions of years of evolution in one of the most extreme environments on Earth. These microbes play a vital role in the Hadal ecosystem. They are the primary decomposers, breaking down the complex organic matter of the marine snow into simpler compounds that can be used by other organisms. They are the engine of the trench's nutrient cycle, ensuring that the limited resources are efficiently recycled. The amphipods and sea cucumbers that graze on the sediment are not just feeding on the dead organic matter itself. They are primarily feeding on the rich film of bacteria that grows on it. The microbes are the crucial link between the non-living and the living world. Furthermore, some of these microbes are chemosynthetic, meaning they can derive energy from chemical reactions rather than from sunlight. In the Hadal zone, this is particularly important at sites of geological activity, such as the serpentinite mud volcanoes. Here, fluids rich in methane and hydrogen seep from the seafloor. Specialized microbes are able to eat these chemicals, using them to produce organic matter. These chemosynthetic microbes form the base of a unique food web that is completely independent of the sunlit world above. The discovery of these ecosystems has profound implications for the search for life on other planets, as it suggests that life could arise and persist on worlds that are far from their parent star, powered by the internal chemical energy of the planet itself. The study of the microbial world of the Mariana Trench is still in its infancy. Every sample brought back from these depths reveals new species, new genes, and new possibilities. These tiny organisms are the unsung heroes of the Hadal zone. They are the engineers of its ecosystem, the drivers of its chemistry, and the ultimate survivors in a world of extremes. They are a powerful reminder that the most significant forms of life on our planet are not always the largest or the most complex, but are often the smallest, the most adaptable, and the most resilient. Bioluminescence. In the perpetual and absolute darkness of the deep ocean, a different kind of light has evolved. It is not the light of the sun, but a cold and living light, generated by the organisms themselves. This is bioluminescence, the production and emission of light by a living organism. And it is one of the most common and most spectacular adaptations to life in the deep sea. In the Hadal zone of the Mariana Trench, where no sunlight can penetrate, this living light plays a crucial role in the struggle for survival. An astonishingly high percentage of deep-sea animals, estimated to be over 75%, are bioluminescent. This is not a rare or unusual trait, but a fundamental aspect of the deep-sea ecosystem. The ability to produce light has evolved independently many times in many different groups of organisms, a powerful example of convergent evolution. This suggests that in a world without sunlight, the ability to make your own light provides a significant evolutionary advantage. The chemistry of bioluminescence is a beautiful and efficient process. It involves a chemical reaction in which a light-emitting molecule, called a luciferin, is oxidized by an enzyme called a luciferase. This reaction releases energy in the form of a photon of light. It is a highly efficient process, with very little energy being lost as a heat. It is a cold light, perfectly suited to the cold environment of the deep sea. The uses of this living light are as varied and as fascinating as the creatures that produce it. For many animals, bioluminescence is a tool for predation. The most famous example is the deep-sea anglerfish. This fearsome predator has a long, fleshy filament growing from its head, at the tip of which is a symbiotic colony of bioluminescent bacteria. The anglerfish dangles this glowing lure in front of its massive mouth, attracting smaller fish and crustaceans to their doom. It is a deadly and effective trap in the darkness. Other animals use bioluminescence for defense. When threatened, some species of deep-sea shrimp and squid can release a cloud of bioluminescent fluid, a glowing smokescreen that can startle and confuse a predator, allowing the animal to escape. This is the deep-sea equivalent of a squid's ink cloud. Other animals use a technique called counter-illumination. They have light-producing organs, called photophores, on their undersides. They can adjust the brightness of these photophores to match the faint, downwelling light from the surface, effectively erasing their own shadow and making them invisible to predators looking up from below. Bioluminescence is also a crucial tool for communication. In the vast and dark expanse of the deep ocean, finding a mate can be a significant challenge. Many species have evolved unique patterns of photophores, which they can flash in specific sequences. These light patterns act as a recognition signal, allowing males and females of the same species to find each other in the darkness. It is a silent and beautiful language of light. Even in the Hadal zone, where the diversity of large animals is lower, bioluminescence is thought to play a role. While it is difficult to observe these animals in their natural environment, many of the crustaceans and other invertebrates found in the trench are believed to be bioluminescent. The light they produce may be used to attract prey, to deter predators, or to communicate with each other in the crushing darkness. The study of bioluminescence is not just a fascinating window into the world of the deep sea. It also has significant implications for science and medicine. The genes for luciferin and luciferase have become powerful tools in molecular biology. Scientists can attach these genes to other genes of interest, and the production of light then acts as a marker, allowing them to visualize and track complex biological processes in real time. The cold and efficient light of the deep sea is now illuminating the inner workings of the human body. Bioluminescence is a testament to the creative power of evolution. It is a beautiful and complex adaptation that has transformed the dark and seemingly empty world of the deep ocean into a vibrant and dynamic realm of living light. It is a reminder that even in the most extreme and challenging environments on our planet, life has found a way to create its own suns, to illuminate its own world, and to fill the darkness with a strange and wonderful and living glow. The Dumbo octopus. Among the many strange and wonderful creatures that inhabit the deep ocean, few are as captivating and as endearing as the Dumbo octopus. Named for the prominent, ear-like fins that protrude from the sides of its head, this group of deep-sea octopuses, belonging to the genus Grimpoteuthis, has become an unlikely ambassador for the mysterious world of the abyss. Its charming appearance, however, belies a creature that is a master of survival, perfectly adapted to a life of extreme pressure and cold. The Dumbo octopus is not a single species, but a genus of about 15 known species. They are found in the deep oceans worldwide, typically at depths of 3,000 to 4,000 meters, though some have been observed as deep as 7,000 meters, in the upper reaches of the Hadal zone. They are the deepest living of all known octopuses. The most distinctive feature of the Dumbo octopus is, of course, its large fins. These are not for hearing, but for propulsion. The octopus flaps these fins slowly and gracefully to move through the water, a motion that has been compared to a flying elephant. This is its primary mode of locomotion, and it is a very energy-efficient way to travel in the still and cold waters of the deep. It can also use its webbed arms to create a kind of umbrella, and by pulsing this web, it can generate a jet of water for a quick burst of speed. Like many deep-sea creatures, the body of the Dumbo octopus is soft and gelatinous. This high water content helps it to cope with the immense pressure of its environment. It lacks the large, rigid internal shell, or gladius, that is found in many other cephalopods. Its body is almost entirely soft tissue, which is less susceptible to being crushed by the pressure. The lack of a rigid structure also allows it to be neutrally buoyant, meaning it can hover in the water column with very little effort. The Dumbo octopus is a predator, but it is not a particularly active one. It spends much of its time hovering just above the sea floor, its webbed arms spread out, waiting for prey to come within reach. Its diet consists of small crustaceans, worms, and other invertebrates that live in the sediment. When it detects a prey item, it can pounce on it, trapping it within its webbed arms before consuming it with its sharp beak. It is a patient and opportunistic hunter. Unlike most other octopuses, the Dumbo octopus does not have an ink sac. In the perpetual darkness of the deep sea, a cloud of ink would be an ineffective defense mechanism. Instead, it relies on its ability to move quickly and on its cryptic coloration to avoid predators, which in its environment would likely be large, deep-sea fish or sharks. Reproduction in the Dumbo octopus is also adapted to the challenges of deep-sea life. Finding a mate in the vast and sparsely populated expanse of the abyss can be difficult. As a result, the female Dumbo octopus is thought to carry eggs in various stages of development at all times. This means that whenever she encounters a male, she can be ready to fertilize her most mature eggs. She then lays these eggs one at a time, attaching them to rocks or other hard surfaces on the sea floor. The young hatch as fully formed, miniature versions of the adults, ready to begin their own life in the deep. The Dumbo octopus is a creature that defies our expectations of what an octopus should be. It is not the cunning and fast-moving predator of the shallow reefs. It is a slow and graceful and almost ethereal creature, perfectly in tune with its calm and dark, dark and silent world. Its existence is a beautiful example of how evolution can shape an animal to fit a specific and extreme niche. It is a reminder that the deep ocean is not a world of monsters, but a world of survivors, a world of strange and beautiful and perfectly adapted life. The Dumbo octopus, with its gentle and almost whimsical appearance, is a powerful symbol of the hidden beauty and the profound mystery of the deep sea. The Mariana snailfish. In the extreme environment of the Mariana Trench, where the pressure is over 1,000 times that of the surface, the very existence of complex, vertebrate life seems impossible. The immense force of the water column should crush bones, deform proteins, and render the delicate machinery of life inoperable. And yet, life has found a way. In 2014, scientists exploring the trench made a remarkable discovery. They filmed a small, translucent, and almost ghostly fish swimming at a depth of 8,145 meters. This was the Mariana snailfish, Pseudoleparis suirae, and it holds the record for the deepest living fish ever found. Its existence is a profound testament to the resilience of life, and it provides a unique window into the biochemical adaptations that are necessary to survive at the very edge of the habitable world. The Mariana snailfish is not a creature of fearsome appearance. It is a small, tadpole-shaped fish, about the size of a human hand. Its skin is thin and translucent, with no scales, giving it a pale, almost ethereal look. Its eyes are small and not very well developed, a common trait in animals that live in a world without light. It is a member of the snailfish family, a group of fish that are known for their soft, gelatinous bodies, a feature that is taken to the extreme in this hadal species. The key to the Mariana snailfish's survival is its ability to cope with the immense pressure. Its body is a masterpiece of biochemical engineering, a collection of adaptations that allow it to thrive in an environment that would be instantly lethal to almost any other fish. Firstly, it has no swim bladder. This gas-filled organ, which most fish use to control their buoyancy, would be crushed flat by the pressure of the deep. Instead, the snailfish achieves neutral buoyancy through its gelatinous, high water content flesh, which is less dense than the surrounding water. Its skeleton is also highly adapted. The bones of the Mariana snailfish are not fully ossified, meaning they are not hard and brittle like the bones of a surface fish. Instead, they are made of a more flexible cartilage. This allows the skeleton to bend and deform under pressure without breaking. The skull, in particular, is not a solid, fused structure, but is composed of many small, loosely connected pieces of cartilage, allowing it to be compressed without being damaged. But the most important adaptations are at the molecular level. The immense pressure of the Hadal zone can force water into the active sites of proteins, altering their shape and preventing them from functioning correctly. To counteract this, the cells of the Mariana snailfish are filled with high concentrations of a special type of molecule called a piazzolite. The most important of these is trimethylamine N-oxide, or TMAO. This small organic molecule works by ordering the water molecules around the proteins, effectively pushing water out of the protein's interior and allowing it to maintain its correct, functional shape. The higher the pressure, the more TMAO is needed. The Mariana snailfish has the highest concentration of TMAO ever measured in any fish, a direct adaptation to its extreme pressure environment. This reliance on TMAO, however, also appears to set a fundamental limit on how deep fish can live. As a fish goes deeper, it needs more and more TMAO to stabilize its proteins. But at a certain point, the concentration of TMAO in the cells becomes so high that it starts to disrupt other cellular processes. The water in the cells becomes so ordered by the TMAO that it can no longer function as a solvent for other molecules. Scientists have calculated that this limit is reached at a depth of about 8,200 to 8,400 meters. This theoretical limit, known as the Hadal paradox, perfectly matches the observational evidence. Fish are found in abundance down to about 8,000 meters, but no fish has ever been seen deeper than the record set by the Mariana snailfish. It seems that even with its remarkable suite of adaptations, the snailfish is living at the absolute physiological limit for vertebrate life. The Mariana snailfish is the top predator in its ecosystem. It feeds on the vast swarms of small amphipods that populate the trench floor. It is a slow and patient hunter, using its sensitive nose and the sensory pores on its head to detect the movement of its prey in the darkness. Its existence proves that a complex and active food web can exist even in the most extreme environment on our planet. It is a symbol of the tenacity of life, a beautiful and ghostly survivor at the bottom of the world. The pressure barrier. The discovery of the Mariana snailfish, thriving at depths of over 8,000 meters, was a landmark in marine biology. It represented a new record for vertebrate life, a testament to the remarkable ability of organisms to adapt to the most extreme conditions imaginable. And yet, this discovery also illuminated a profound and invisible boundary, a line in the abyss beyond which a certain kind of life does not seem to exist. The Mariana snailfish is not just a survivor, it is a sentinel, marking the very edge of the vertebrate world. Below the depths where it roams, there appears to be a pressure barrier, a fundamental limit imposed by physics and biochemistry that fish, no matter how well adapted, cannot cross. For decades, oceanographers have observed a consistent pattern in the distribution of life in the deep ocean. As one goes deeper, the abundance and diversity of fish decline. In the Hadal zone, below 6,000 meters, only a few highly specialized species, like the snailfish, are found. But below about 8,200 to 8,400 meters, they disappear entirely. Extensive surveys of the deepest parts of the trenches, using baited cameras and robotic vehicles, have revealed a world teeming with crustaceans and other invertebrates, but conspicuously devoid of fish. This is not an accident of sampling. It is a fundamental ecological and physiological boundary. The reason for this barrier lies in the intricate and delicate dance of molecules within the living cell. The machinery of life is built from proteins, complex, three-dimensional molecules that must maintain a precise shape to function correctly. They are the enzymes that catalyze chemical reactions, the structural components that give cells their form, and the motors that allow them to move. Under the immense pressures of the Hadal zone, these delicate structures are under constant assault. Pressure forces water molecules into the small cavities and crevices within a protein structure, disrupting the subtle chemical bonds that hold it in its correct shape. This causes the protein to unfold, or denature, rendering it useless. It is the same process that occurs when you cook an egg. The heat causes the proteins in the egg white to denature and solidify. In the deep sea, pressure has the same destructive effect. To counteract this, deep-sea organisms have evolved a powerful defense mechanism. Their cells are filled with high concentrations of small organic molecules called piezolites, or pressure resistors. The most important of these for marine fish is trimethylamine N-oxide, or TMAO. This molecule works by structuring the water around the proteins, effectively creating a protective shell that prevents the external pressure from forcing water into the protein's interior. TMAO stabilizes the protein, allowing it to maintain its functional shape even under thousands of atmospheres of pressure. The deeper a fish lives, the more pressure it experiences, and therefore the more TMAO it needs in its cells to keep its proteins from denaturing. The concentration of TMAO in the tissues of deep-sea fish increases almost linearly with depth. The Mariana snailfish, living at over 8,000 meters, has the highest concentration of TMAO ever measured in a fish. It is saturated with the stuff. And herein lies the paradox. While TMAO is essential for life at depth, it also has a downside. At very high concentrations, it begins to alter the fundamental properties of the water within the cell. The water becomes so highly structured by the TMAO molecules that it can no longer act as an effective solvent for other biological processes. The very solution that life has evolved to cope with pressure becomes, at a certain point, incompatible with life itself. Scientists have calculated the theoretical depth at which this limit is reached. It is the point where the concentration of TMAO required to stabilize proteins would be so high that the cell's internal environment would cease to function. That calculated depth is approximately 8,400 meters. This theoretical prediction matches the observational evidence perfectly. The pressure barrier for fish is not a physical wall, but a biochemical one. It is the point at which the cost of adaptation becomes too high. The point at which the solution to one problem creates another, insurmountable one. But this barrier is not an end to life. It is merely a filter. While vertebrates like fish, with their complex physiology and highly sensitive proteins, cannot seem to cross this line, other, simpler forms of life can and do. Below 8,400 meters, the ecosystem of the Mariana Trench changes. The reign of the fish ends, and the reign of the invertebrates and the microbes begins. The dominant life forms in the deepest parts of the trench are the amphipods. These small crustaceans are found in incredible numbers, swarming over the sea floor. Their physiology is fundamentally different from that of fish, and they appear to have evolved a different and perhaps more effective set of strategies for coping with extreme pressure. Their success in the deepest parts of the Hadal zone is a testament to the evolutionary ingenuity of the arthropod body plan. Alongside the amphipods are other invertebrates, such as sea cucumbers and worms, as well as a vast and largely unexplored world of single-celled organisms. Foraminifera, a type of shelled amoeba, build their intricate calcium carbonate shells on the seafloor, apparently untroubled by the pressure. And everywhere, in the water and in the sediment, are the bacteria and archaea, the true masters of extreme environments, their simple cellular structure and robust biochemistry allowing them to thrive where more complex life cannot. The pressure barrier is a profound lesson in the nature of life on Earth. It demonstrates that even the most successful and adaptable groups of animals have their limits. Limits that are set by the fundamental laws of physics and chemistry. But it also shows that where one form of life reaches its boundary, another is ready to take its place. The deepest parts of the Mariana Trench are not a void, but a different kind of world. A world ruled not by the fish, but by the humble and incredibly resilient invertebrate and the microbe. Sounds of the abyss. The deep ocean is often imagined as a silent world. The absence of light and the immense pressure create an environment that feels remote and disconnected from the familiar, sound-filled world of the surface. But this perception is misleading. The Mariana Trench, like all parts of the ocean, is filled with a rich and complex soundscape. Sound travels remarkably well in water, far better than it does in air. And the deep ocean is a conduit for a host of natural and, increasingly, artificial sounds. Listening to this soundscape through the use of sensitive underwater microphones called hydrophones provides a unique and powerful way to study the deepest parts of our planet. The ambient sound of the deep ocean is a constant, low-frequency hum. This is the sound of the Earth itself, the background noise of a geologically active planet. It is the sound of distant earthquakes, their seismic energy converted into acoustic waves that can travel for thousands of kilometers through the deep sound channel of the ocean. It is the sound of underwater volcanic eruptions, of submarine landslides, and of the constant, slow grind of tectonic plates. In 2015, a team of researchers from the National Oceanic and Atmospheric Administration, NOAA, and Oregon State University undertook a bold experiment. They deployed a titanium-encased hydrophone to the bottom of the Challenger Deep, leaving it to record for 23 days. The goal was to measure the baseline sound levels in the deepest part of the ocean, to understand what this remote and seemingly isolated environment sounds like. The results were surprising. The trench was not a quiet, peaceful oasis. It was a noisy place. The hydrophone captured the constant rumble of distant earthquakes, a reminder of the trench's location on the seismically active Pacific Ring of Fire. It recorded the distinct sound of a Category 4 typhoon passing overhead, its powerful winds and waves creating a cacophony that was clearly audible even 11 kilometers below the surface. And it picked up the sounds of life. The most prominent biological sounds were the calls of whales. The hydrophone recorded the complex and haunting songs of baleen whales, likely fin whales or minke whales. These low-frequency calls can travel for immense distances through the ocean, and their presence in the Challenger Deep demonstrates the interconnectedness of the entire ocean ecosystem. The deepest point on Earth is not isolated from the great migrations and the social lives of the planet's largest animals. The hydrophone also recorded the high-frequency clicks of odontocetes, or toothed whales. likely a pod of dolphins or small pilot whales passing somewhere in the waters far above. These sounds, used for echolocation, are another thread in the rich and complex tapestry of the ocean's acoustic world, but the recordings also contained a more troubling sound. Amidst the natural chorus of earthquakes and whales, the hydrophone clearly and consistently picked up the noise of human activity. The most common sound was the low-frequency drone of ship propellers. The Mariana Trench lies close to major shipping lanes in the Western Pacific, and the sound of these vessels, passing many kilometers away on the surface, was a constant presence in the recordings. The acoustic footprint of our global economy, it seems, extends to the very bottom of the sea. This discovery has profound implications. It demonstrates that no part of our planet is truly untouched by human influence. The noise pollution that we are introducing into the oceans is a global phenomenon, and it has the potential to disrupt the lives of marine animals that rely on sound for communication, for navigation, and for finding food. For animals that have evolved over millions of years in a relatively quiet, natural soundscape, the constant and growing intrusion of anthropogenic noise is a new and significant environmental stressor. The study of the sounds of the abyss is a relatively new field of oceanography, but it is one that holds immense promise. By listening to the ocean, we can monitor the health of marine ecosystems, track the movements of endangered species, and study the geological processes that shape our planet. The soundscape of the Mariana Trench is a complex and beautiful and sometimes disturbing symphony. It is the sound of a living planet, a planet of immense natural power, and a planet that is being profoundly and irrevocably changed by the activities of a single species. It is the sound of our world, in all its beauty and all its fragility. The mud volcanoes. The geology of the Mariana Trench is dominated by the great and destructive process of subduction, but this process also gives rise to another, more mysterious and creative geological feature: the serpentinite mud volcanoes. These are not true volcanoes that erupt molten lava, but strange and complex systems where fluids and mud from deep within the Earth's crust are forced to the surface. They are oases of chemical activity in the deep ocean, and they support unique ecosystems that are providing new insights into the origin of life on Earth and the potential for life on other worlds. These mud volcanoes are found on the overriding Mariana Plate in the forearc region between the Trench and the Mariana Islands. They are formed by a unique combination of factors related to the subduction process. As the Pacific Plate is forced downward, the water trapped in its rocks is heated and released. This hot and chemically altered fluid rises and interacts with the rock of the overlying mantle wedge. This interaction triggers a chemical reaction called serpentinization. Serpentinization is the process by which olivine, a common mineral in the Earth's mantle, is converted into serpentine minerals. This reaction releases a significant amount of heat, and it produces a host of other chemical compounds, including hydrogen gas, methane, and highly alkaline fluids. The serpentine minerals are also much less dense than the original mantle rock. This mixture of low-density minerals, hot fluids, and gases is buoyant, and it rises toward the seafloor, eventually erupting to form a mud volcano. These are colossal structures, some of them reaching over 50 kilometers in diameter and rising over 2 kilometers from the seafloor. They are built up over thousands of years by the slow and steady eruption of a cold and fluid serpentine mud. The fluids that emanate from these mud volcanoes are unlike anything else found in the ocean. They are extremely alkaline, with a pH as high as 12.5, similar to that of household bleach. They are also rich in dissolved hydrogen and methane. This unique chemical environment, while hostile to most forms of life, is a paradise for a specific type of microbe, the chemosynthesizer. Chemosynthetic microbes are able to derive energy not from sunlight, but from chemical reactions. The bacteria and archaea that live at the serpentinite mud volcanoes are specialists in consuming the hydrogen and methane in the vent fluids. They are the primary producers in this ecosystem, forming the base of a food web that is completely independent of the sun. They are, in essence, living off the chemical energy of the Earth itself. This has profound implications for our understanding of the origin of life. Some scientists believe that life on Earth may have originated in a similar, alkaline hydrothermal environment. The chemical reactions that occur during serpentinization can produce not just hydrogen and methane, but also simple organic molecules, the building blocks of life. The serpentinite mud volcanoes of the Mariana Forearc are, in this view, a modern-day analog for the kind of environment that may have given rise to the first living cells on our planet. Recent discoveries have only deepened this connection. In 2023, a strange, blue, gooey substance was collected from one of these mud volcanoes. Analysis of this blue goo revealed that it was rich in lipid biomarkers, the fatty molecules that make up the cell membranes of living organisms. These biomarkers were indicative of a thriving community of bacteria and archaea living within the serpentine mud. It was a powerful confirmation that these mud volcanoes are indeed a significant and active deep-sea biosphere. The study of these ecosystems also has major implications for astrobiology, the search for life on other worlds. The chemical processes of serpentinization are thought to be common on other rocky bodies in our solar system. For example, the plumes of water erupting from Saturn's moon Enceladus have been found to be rich in hydrogen and other compounds that are consistent with active serpentinization in its subsurface ocean. The serpentinite mud volcanoes of the Mariana Trench are a natural laboratory for studying the kind of life that might exist in these dark and distant oceans. The mud volcanoes are a world of their own, a strange and beautiful and chemically exotic realm that exists in the shadow of the Great Mariana Trench. They are a testament to the complex and often surprising ways in which geology and biology are intertwined. They are a window into the deep workings of our planet, a clue to the origin of life on Earth, and a beacon of hope in the search for life elsewhere in the universe. Pollution in Paradise Lost. The Mariana Trench has long been a symbol of the pristine and untouched wilderness of our planet. Its extreme depth, its remoteness, and its hostile environment have created a perception of a realm that is beyond the reach of human influence, a final and perfect sanctuary from the ever-expanding footprint of our industrial world. But this perception, like so many of our romantic notions about the natural world, has been shattered. In recent years, a series of shocking discoveries has revealed that even the deepest, most remote place on Earth is not immune to our pollution. The Mariana Trench, it turns out, is acting as a sink for the toxic legacy of our modern civilization. In 2019, the explorer Victor Vescovo made a record-breaking dive to the bottom of the Challenger Deep. Peering out of the porthole of his submersible, he saw what he described as a plastic bag and candy wrappers. The discovery made headlines around the world. It was a stark and visceral symbol of the global plastic pollution crisis. The fact that our disposable, single-use waste had reached the most inaccessible point on the planet was a sobering wake-up call. But the problem goes far deeper than just visible pieces of plastic. The real threat is from microplastics, the tiny, often invisible particles of plastic that are created when larger plastic items break down. These particles are now ubiquitous in the global ocean, and they are finding their way into the Huddle food web. A 2019 study found that every single amphipod collected from the Mariana Trench, from depths of 6,000 to 11,000 meters, had ingested microplastics. The fibers from plastic bottles, packaging, and synthetic clothing are being consumed by the most basic organisms in the trench's ecosystem. This has profound implications. As these small animals are eaten by larger ones, the plastic is transferred up the food chain, a process known as bioaccumulation. The long-term effects of this plastic ingestion on deep-sea organisms are not yet known, but it is likely to be harmful. The plastic particles themselves can cause physical damage to the digestive tracts of small animals, and they can also leach toxic chemicals. And it is not just plastic. The Mariana Trench is also accumulating a host of other persistent organic pollutants, or POPs. These are industrial chemicals, such as polychlorinated biphenyls, PCBs, and polybrominated diphenyl ethers, PBDEs, which were widely used in the 20th century as coolants, lubricants, and flame retardants. These chemicals are highly toxic, and they do not break down easily in the environment. They were banned most decades ago, but their legacy endures. These chemicals find their way into the ocean through industrial discharge, agricultural runoff, and atmospheric deposition. Once in the ocean, they tend to bind to organic particles. As the marine snow sinks through the water column, it effectively scavenges these pollutants from the surface waters and transports them to the deep sea. The funnel-like shape of the trench then acts to concentrate this contaminated material on the seafloor. A 2017 study found that the concentration of PCBs in the fatty tissues of amphipods from the Mariana Trench was up to 50 times higher than in crabs from one of the most polluted rivers in China. The deepest, most remote place on Earth, it turns out, is one of the most polluted. The trench is acting as a chemical sink, a final resting place for some of the most toxic substances ever created by humanity. This discovery is a stark illustration of the interconnectedness of our planet's systems. There is no away. The waste that we produce, the chemicals that we release, do not simply disappear. They are transported by ocean currents and atmospheric winds, and they are accumulating in the most remote and seemingly pristine environments on Earth. The deep ocean, once thought to be a stable and unchanging realm, is now known to be intimately connected to the surface world, and it is feeling the effects of our actions. The pollution of the Mariana Trench is a profound and tragic loss. It is the loss of a wilderness that we are only just beginning to explore. It is a threat to a unique and fragile ecosystem that we are only just beginning to understand. And it is a powerful and humbling reminder of the immense responsibility that we have as the dominant species on this planet. The fate of the deepest, darkest corners of our world is inextricably linked to the choices that we make in the sunlit world above. Comparing extremes, humanity has always been driven by a desire to explore the unknown, to push the boundaries of our world and to venture into realms that are hostile to our existence. In the 20th and 21st centuries, this ambition has been focused on two great and opposing frontiers: the vacuum of outer space and the crushing pressure of the deep ocean. The journey to the moon and the journey to the bottom of the Mariana Trench are often seen as parallel achievements, twin triumphs of human ingenuity and courage. But a closer comparison reveals that these two frontiers, while both extreme, present fundamentally different and in some ways more difficult challenges. In many respects, the journey to the bottom of our own planet is a more formidable undertaking than the journey to our nearest celestial neighbor. The primary difference lies in the nature of the environment itself. Space is a vacuum. The challenge of space exploration is to build a vessel that can maintain 1 atmosphere of pressure on the inside while being surrounded by 0 pressure on the outside. This is a significant engineering challenge, but it is a one-way pressure differential. The deep ocean, on the other hand, is a realm of immense external pressure. The challenge of Hadal exploration is to build a vessel that can maintain 1 atmosphere on the inside while being subjected to over 100 atmospheres of pressure on the outside. This is a crushing and relentless force that is constantly trying to find a point of failure. This difference in pressure has profound implications for the design of exploratory vehicles. A spacecraft can be a relatively large and complex structure with a thin metal skin. A deep-sea submersible, on the other hand, must be a compact and incredibly robust sphere of solid metal with no weak points. The materials science required to build a vehicle that can withstand the pressure of the Challenger Deep is, in many ways, more demanding than that required to build a lunar lander. Another major difference is the medium of travel. In the vacuum of space, once a spacecraft has escaped Earth's gravity, it can travel with very little resistance. The journey to the moon is a 3-day coast through a near-perfect vacuum. The journey to the bottom of the Mariana Trench is a slow and difficult slog. Through a dense and viscous fluid, the descent and ascent take hours, and the vehicle is constantly battling the drag of the water. This severely limits the amount of time that can be spent on the bottom, and it makes maneuvering and exploration a slow and painstaking process. Visibility is another key distinction. Space is transparent. From the surface of the moon, one can see the Earth, the sun, and the stars with perfect clarity. The deep ocean is a world of absolute darkness. Visibility is limited to the range of a submersible's lights, typically only a few tens of meters. Exploring the Mariana Trench is like exploring a vast and unknown continent at night, with only a small flashlight. It is impossible to get a sense of the larger landscape, and discoveries are often a matter of chance and luck. Communication is also far more difficult in the deep ocean. Radio waves, which are the basis of communication in space, do not travel through water. Communication with a deep-sea submersible must be done through a tethered cable, which is impractical for a free-diving vehicle, or through underwater acoustics. Acoustic communication is very slow, has a very low bandwidth, and is prone to distortion and interference. It is a far cry from the real-time video and audio communication that was possible during the Apollo missions. Finally, there is the question of rescue. In the event of a catastrophic failure in space, there is, tragically, very little that can be done. But for a non-catastrophic failure, such as a loss of power or propulsion, there is at least the theoretical possibility of a rescue mission. In the deep ocean, there is no such possibility. A submersible that is stranded on the bottom of the Mariana Trench is in a place that is more remote and more inaccessible than the surface of the moon. There is no vehicle on Earth that could reach it in time, and no way to retrieve it. The commitment to a dive into the Hadal Zone is absolute. For all these reasons, the deep ocean remains, in many ways, a more challenging frontier than space. While we have sent probes to every planet in our solar system and have mapped the surface of Mars in higher resolution than the floor of our own oceans, the Hadal Zone remains a realm of profound mystery. We have spent more time on the surface of the moon than we have on the bottom of the Challenger Deep. The comparison between these two great journeys of exploration is not meant to diminish the incredible achievements of the space program. but to highlight the unique and often underappreciated challenges of exploring our own planet's final frontier. The journey to the bottom of the sea is a journey into a world that is, in many ways, more alien and more hostile than any other in our solar system. Other ocean trenches. The Mariana Trench, with its record-breaking depth, holds a special place in the human imagination. But it is not a unique feature. It is part of a global system of deep-sea trenches, a network of profound chasms that mark the boundaries where the Earth's tectonic plates are in collision. There are over 30 such trenches in the world's oceans, and each one is a unique geological and biological realm. To understand the Mariana Trench in its proper context, we must see it as one member of a family of deep-sea giants, each with its own story and its own secrets. All ocean trenches are formed by the same fundamental process: subduction. But the specific characteristics of each trench, its depth, its shape, its seismic activity, and its biological communities, are determined by a host of local factors, such as the age of the subducting plate, the angle of subduction, and the rate of convergence between the two plates. The second deepest trench in the world is the Tonga Trench, located in the Southwest Pacific Ocean. It reaches a maximum depth of 10,882 meters, only about 100 meters shallower than the Challenger Deep. The Tonga Trench is known for having the fastest moving tectonic plate on Earth. The Pacific Plate is converging with the Tonga Plate at a rate of up to 24 centimeters per year. This rapid convergence makes the Tonga Trench one of the most seismically active places on the planet, with frequent and powerful earthquakes. To the north of the Tonga Trench lies the Kermadec Trench, another immense hadal system. It is part of the same subduction zone as the Tonga Trench, and it reaches a depth of over 10,000 meters. The Kermadec Trench is home to a unique community of deep sea life, including a species of giant amphipod that is distinct from those found in the Mariana Trench. This highlights the high degree of endemism in hadal ecosystems. The isolation of each trench has allowed for the evolution of unique species. In the Northwest Pacific, the Japan Trench and the Kuril-Kamchatka Trench are two other major hadal systems. These trenches are formed by the subduction of the Pacific Plate beneath the Eurasian Plate. They are both over 10,000 meters deep, and they are both associated with intense volcanic and seismic activity. The 2011 Tohoku earthquake, which caused the devastating tsunami in Japan, originated in the subduction zone of the Japan Trench. This is a powerful and tragic reminder of the immense geological forces that are at play in these regions. Not all trenches are in the Pacific. The Puerto Rico Trench in the Atlantic Ocean is the deepest point in that ocean at over 8,300 meters. It is a complex geological feature formed by a combination of subduction and transform faulting. The Java Trench in the Indian Ocean is another major hadal system, and it was the source of the 2004 Indian Ocean earthquake and tsunami, one of the deadliest natural disasters in recorded history. Each of these trenches is a unique natural laboratory. By comparing the geology, the chemistry, and the biology of different trenches, scientists can begin to understand the general principles that govern hadal ecosystems, and the specific factors that lead to the unique characteristics of each one. For example, the amount of food that reaches the bottom of a trench is influenced by the productivity of the surface waters above it. Trenches that are located beneath nutrient-rich waters, such as the Peru-Chile Trench off the coast of South America, have a much higher biomass of hadal life than trenches that are located beneath the nutrient-poor waters of the open ocean, like the Mariana Trench. This comparative approach has led to a new and more nuanced understanding of the hadal zone. It is not a single, uniform environment, but a mosaic of different habitats, each with its own unique history and its own unique community of life. The Mariana Trench may be the deepest, but it is not the only one. It is one of many worlds in the deep ocean, each one a frontier of exploration and discovery. The global system of ocean trenches is a fundamental feature of our planet's geology. It is the primary site of the recycling of the Earth's crust, a key driver of the planet's chemical cycles, and the home of a unique and largely unexplored biosphere. The Mariana Trench, as the deepest and most extreme example, is a powerful symbol of this hidden world. But it is the study of all the trenches, in all their diversity, that will ultimately reveal the full and complex story of life in the abyss. The future of deep-sea exploration. The exploration of the Mariana Trench and of the Hadal Zone in general is at a turning point. The pioneering dives of the Trieste and the Deep-Sea Challenger have proven that human-crewed exploration of these depths is possible. The robotic missions of vehicles like Kaiko and Nereus have demonstrated the power of uncrewed systems to do science in this extreme environment. But these have been isolated and expensive expeditions. The future of deep-sea exploration lies in making access to the Hadal Zone more routine, more affordable, and more scientifically productive. A new generation of technologies, from autonomous robotics to advanced sensors, is poised to usher in a golden age of Hadal science. The workhorse of future deep-sea exploration will undoubtedly be the Autonomous Underwater Vehicle, or AUV. These are untethered, robotic submarines that can be programmed to carry out a specific mission without direct human control. They are the deep-sea equivalent of the Mars rovers. Future AUVs designed for Hadal exploration will be able to spend days or weeks at a time in the trench, systematically mapping its geology, measuring its chemical properties, and surveying its biological communities. They will be equipped with a suite of miniaturized sensors, high-resolution cameras, and sophisticated software that will allow them to make their own decisions, to identify areas of interest, and to adapt their mission plan in real time. Another key technology will be the Hadal Lander. These are uncrewed stationary platforms that are dropped to the seafloor and left there for extended periods, from days to years. They are the deep-sea equivalent of a weather station or a seismic observatory. A Hadal Lander can be equipped with a wide array of instruments, including cameras to monitor animal behavior, traps to collect biological samples, sensors to measure water chemistry, and hydrophones to listen to the soundscape. By providing a long-term continuous presence on the seafloor, these landers will allow scientists to study the temporal dynamics of the Hadal ecosystem, to observe how it changes over time in response to factors like food falls or seismic events. Advances in material science will also be crucial. The development of new, stronger, and lighter materials, such as ceramic composites and metallic glasses, will allow for the construction of more capable and more resilient deep-sea vehicles. These materials will be used to build pressure housings for electronics, buoyant structures for AUVs, and perhaps even the next generation of human-occupied spheres. The role of artificial intelligence and machine learning will also be transformative. The vast amounts of data that will be collected by these new robotic systems, hours of high-definition video, detailed chemical analyses, continuous acoustic recordings, will be impossible for humans to analyze manually. AI algorithms will be needed to automatically identify animals in video footage, to detect patterns in chemical data, and to classify sounds in acoustic recordings. AI will be the key to turning the flood of raw data from the deep sea into meaningful scientific knowledge. But the future of deep-sea exploration is not just about robots. There is still a powerful and compelling case to be made for human presence. The intuitive ability of a human observer to spot something unusual, to make a connection between disparate pieces of information, and to convey the wonder and the excitement of discovery is something that no robot can yet replicate. The future of human-crewed Hadal exploration will likely involve a new generation of submersibles, perhaps with transparent, acrylic hulls that provide a panoramic view of the abyss. These vehicles will be designed not just for exploration, but for science, with advanced manipulators for collecting samples and a suite of integrated sensors. One of the most exciting future prospects is the establishment of a permanent deep-sea observatory in the Mariana Trench. This would be a network of landers, AUVs, and cabled sensors that would provide a continuous, real-time presence in the Hadal zone. It would be connected to the surface by a fiber optic cable, allowing scientists from all over the world to access the data and even to control the instruments in real time. It would be a window into the deep, a permanent outpost of human knowledge in the most remote environment on Earth. The future of deep-sea exploration is a future of synergy, a future where human and robotic explorers work together. Humans will provide the vision, the intuition, and the narrative. Robots will provide the persistence, the precision, and the ability to go to places and to stay for times that are too dangerous or too difficult for humans. Together, they will unlock the secrets of the Hadal zone, and in doing so, they will write the next great chapter in the story of our planet's exploration. The final secret. We have journeyed to the deepest part of our planet, a realm of crushing pressure, perpetual darkness, and profound mystery. We have explored its geography, a landscape of colossal trenches and volcanic arcs. We have delved into its geology, a story of tectonic plates in a slow and powerful collision. We have marveled at its biology, a world of strange and resilient creatures that have adapted to an environment more hostile than the surface of Mars. And we have followed the history of its exploration, a tale of human courage, ingenuity, and the enduring quest to understand our own world. But after all this, what is the ultimate significance of the Mariana Trench? What is the final secret that it has to tell us? The trench is, first and foremost, a powerful symbol of the unknown. In an age where our planet seems to be fully mapped, fully measured, and fully understood, the Hadal zone is a stark and humbling reminder that we live on a world that is still largely unexplored. We know more about the surface of the moon than we do about the bottom of our own oceans. The Mariana Trench represents the vastness of our own ignorance, the immense and exciting frontiers of discovery that still await us on our own planet. It is also a profound lesson in the nature of life itself. The existence of a thriving ecosystem in the Mariana Trench forces us to expand our definition of what is possible for life. It demonstrates that life is not a fragile and delicate flame that can exist only in the warm and sunlit surface world. It is a tenacious and creative and incredibly resilient force, capable of adapting to the most extreme conditions imaginable. The creatures of the trench, from the pressure-loving microbes to the ghostly snailfish, are a testament to the power of natural selection to find solutions to even the most formidable environmental challenges. They are a source of inspiration and a cause for a deep and abiding sense of wonder at the ingenuity of the natural world. Furthermore, the trench is a window into the deep and interconnected workings of our planet. It is not an isolated and static feature. It is a key component of the Earth's great geological and chemical cycles. It is a place where the planet's crust is recycled, where the chemical balance of the oceans is regulated, and where the fundamental forces that shape our world are on full display. To study the trench is to study the very engine of our planet, to gain a deeper understanding of the complex and dynamic system that makes our world a habitable one. But perhaps the most important secret that the Mariana Trench has to reveal is a more personal and a more urgent one. It is a secret about ourselves. The discovery of plastic waste and industrial pollutants in the deepest, most remote part of our planet is a moment of profound and uncomfortable self-reflection. It is the moment we realize that there is no way. It is the moment we understand that the health of the entire planet, from the highest mountains to the deepest trenches, is inextricably linked to our own actions. The Mariana Trench, in this sense, is the ultimate canary in the coal mine. If our pollution has reached this remote and seemingly pristine sanctuary, then it has reached everywhere. The trench is a mirror, reflecting back to us the global consequences of our consumption, our waste, and our disregard for the natural world. It is a call to a new kind of exploration, an exploration not of the external world, but of our own relationship with our planet. It is a call to a new sense of stewardship, a recognition that we have a profound responsibility to protect the entire Earth system, from the familiar landscapes of the surface to the hidden and mysterious worlds of the deep. The final secret of the Mariana Trench, then, is not a single, simple fact. It is a complex and multifaceted truth. It is the truth of our own ignorance, the truth of life's incredible resilience, the truth of our planet's deep interconnectedness, and the truth of our own and undeniable impact. The journey to the bottom of the sea is, in the end, a journey back to ourselves. It is a journey that forces us to confront our place in the natural world and to ask the most important question of all: what kind of planet do we want to live on? And what kind of ancestors do we want to be?